We're getting into sequences and series. 12.1, a sequence or a numerical pattern is actually a function. You could actually think of it as a function, and in calculus that could be especially helpful. We can talk more about that in just a moment. But look, you'll be given a formula. This is known as an explicit formula. It's a formula that very powerfully will allow you to find whatever term was asked for. Generally, we'll start with the first term, of course. That's where n would equal 1. And if n were to equal 1, 1 squared minus 1, well, that's 1 minus 1. It's 0. And we'd say, well, what's our second term? Plug in a 2. 2 squared is 4. 4 minus 1 is 3. Plug in a third term. N equals 3. 3 squared is 9. 9 minus 1 is 8. Fourth term. Well, plug in a 4. 4 squared is 16. 16 minus 1 is 15. And finally, for a fifth term, 5 squared is 25. 25 minus 1 is 24. Now, the explicit formula also gives you the huge advantage, too, of being able to find whatever term would be asked for. If all of a sudden I said, quick now, tell me the 100th term, you'd say, well, I'll just plug in 100, 100 squared minus 1, and that would be it. Not all forms have that benefit, but for right now, we're good. Now, I do want to talk just one more little bit about the fact that this is a function, because it can help you, or the students especially who are moving on to BC next year. So look, your first term, you could look at this as an ordered pair, like 1 comma 0. Your second term, you could say 2 comma 3. Third term, you could call that 3 comma 8, 4 comma 15, and 5 comma 24. Your book is not asking you to do that, but it's good for you to see it right now. By the way, you could graph those. And I think many students might be wondering at this point, wow, do you really mean to call that a function? I mean, really, when you think about functions, you think about, parabolas and, sine waves and all these other things that we've been studying. And you're saying, look, you've got a select number of ordered pairs. Would that be a function? Here's my question to you. Does it pass the vertical line test? Yes. So this could be a function. This could be a function, and it is a function. But that being said, what you're going to do on your homework is more or less just make a list like this. Well, let's move on. Look, your functions might involve negatives. Negative 1 to the n, you could say, what's your first term? Well, plug in a 1. Negative 1 to the first is something negative. Now look at this. N is 1, and down below 1 plus 1 is 2. You'd have a negative 1 all over 2. How about a second term? Plug in a 2. Negative 1 squared is positive. And then you could say plug in a 2. 2 all over 2 plus 1 is 3. You'd say I have a positive 2/3. Now it doesn't take too long for kids to notice that your denominator is always one step bigger than your numerator. And we are alternating. By the way, you can see up on the board, or perhaps behind the screen, we were dealing with alternating series in calculus today, where this exact behavior was occurring, where you're moving from negatives to positives, and so forth. So, wow, our third term, well, you'd say, negative 1 cubed, that's something negative. 3 all over 3 plus 1 is 4. Pretty soon, kids begin to say, hey, I know what my next term is. I don't need for you to tell me. I see the pattern. It's going to be positive. You get positive 4/5. Next one, negative 5 over 6. You can notice the pattern. Now, I'm trying to stress pattern recognition because that's where we're moving next. Okay, so let's take a look at some problems that you'll have in your homework. And this can get a little more thought-provoking, where instead of giving you an explicit formula and asking you to generate 5 terms, they'll say, hey, here are 4 or 5 terms, give me the formula. Wow. Well, we need to do some thinking here. And this might take a little bit more effort. But look at your numerator. Just pay attention to your numerator for starters. 2, 4, 8, 16. Tell me about it. They're all dealing with 2. What about 2? Powers of 2. Not multiples of 2. Multiples of 2 would be 2 times 1, 2 times 2, 2 times 3. Notice there's no 6 up there, right? And all of a sudden you say, no, wait a minute. This is 2 to the first, 2 to the second, 2 to the third. Aha, this is my third term. Wow, look at that. Fourth term, I get 2 to the fourth. Interesting. Down below, do we notice anything? Powers of 3. Look at that. 3 to the first, 3 to the second, 3 to the third. And sometimes kids might even want to say, ooh, let's double check and make sure that is in fact a power of 3. Indeed it is. What do you think our formula might be? 2 to the n divided by 3 to the n. Now some of you might say, ooh, is it okay to write 2/3 to the n? Oh, that would be equivalent, wouldn't it? Okay, so this might be a little bit different. I don't think we work this way as much, but hey, this helps you become much more comfortable just with patterns in general. This next one I think is a step more difficult. By the way, Mr. Clifford and I changed the notes this morning because we noticed in our last year notes we didn't really include as many of these, and we want to give you guys some practice on it. So my goodness, I'm looking at this next sequence. I do notice one immediate pattern. The top is always 1. So, hey, stating the obvious, maybe it's not so helpful at first. You'd say, well, at least I know my top should be 1 all the time. But down below, this is where we could get upset. You'd say, oh, 2, and then 6, and then a 12, and then a 20, and a 30. And yeah, they're all even. But they're not powers of 2. And I don't think it's immediately apparent what you're seeing here. Well, look, we are making a video, and I'm trying to be as good with time as we can. Sometimes it can be very helpful to maybe deconstruct a little bit and take a look at just the simple number 6 and say maybe look at 6 a little bit differently as maybe 2 times 3. That's a huge hint. By the way, this is our second term. I heard somebody say, I see. Did somebody see something? Yeah? How might we look at 12? 3 times 4? Wait a minute, that's our third term. Wait a minute, what about our fourth term? Any thoughts? 4 times 5. Oh my gosh, what about the fifth term? 5 times 6. Well, sometimes kids will say, well, does the first term fit that pattern? Oh, indeed it does. Well, wow, maybe just to be exceptionally clear about something, look at that. The third term has a 3 down below. The fourth term is a 4 in it. The fifth term is a 5 and so forth. But even more so than it has the integer after it, doesn't it? How on earth could we write that in a formula? N times n plus 1, indeed. Indeed. So that's what I mean when this might be a little more of a stretch sometimes. They're not all this obscure. Talking about obscure problems, my word. This one can be very obvious to describe the pattern. And by the way, sometimes just trying to guess what the next term would be. Look, 1, 1/2, 3, 1/4, 5, 1/6, end at 1/8. What's the next term? I think we all could say it's 9. I think we all know what's happening, right? Trying to describe it algebraically is the challenge, isn't it? Kids will say, wow, your first term is a 1. Your second term has a 2 in it. Your third term has a 3 in it. Wow. Wow, wow, wow. Dare I say, we're dealing with some reciprocals. What's another way to write any old reciprocal? Like even start with 1/2. What's another way to write 1/2? 2 raised to the oh, so you mean I could go 1, 2 to the negative 1, 3, 4 to the negative 1, 5, 6 to the negative 1, 7, and so on. Well, that's at least a help. It might not seem like it's much of a help, but right now, the base of all my exponents would just be n, wouldn't it? So I'm going to have to take n raised up to a power. The problem is that sometimes we're raising it up to the first power, and then other times we're going to the negative 1 power, positive 1 or negative 1. You can think, oh my gosh, we are so close. We're so amazingly close to this. You'd say, isn't it n raised up to something? Indeed it is. And the question is, how could we create something that's changing from a 1 to a negative 1 to a 1? Wait a minute. Weren't we changing from a negative to a positive, from a negative to a positive before? What was doing that? The negative 1 to the n. Now, let's be careful here, because we want to begin with a positive. And if I just wrote negative 1 to the n, the problem is, as you're getting there, you'd say, well, for my first term, then I'd go negative 1 to the 1, and then it would be negative. You'd think, oh, nuts, that won't work. How do we fix it? Well, maybe instead of saying n, maybe make it n plus or minus 1. You see what I'm saying? So what I'm going to do is I'm going to say this should be negative 1 to the n plus 1, but then we can even put some parentheses around it, essentially saying do what's inside these parentheses first. That's so pertinent to the problem. We want to be very clear that you always do what's inside parentheses first, so that we're going to make sure that my first term, when I plug in a 1, I'm going to do everything inside those yellow brackets. 1 plus 1 is 2. Negative 1 squared is a positive, and then I'll have 1 raised up to that. That would generate that pattern. And just want to be super clear to you, sometimes kids almost wonder, like with the calculator, if that would really work. Like they might say, hey, is this okay? Like if I went 2 raised to that, like let's work out our second term. And you'd say, well, I'd need parentheses. I'd need negative 1. Oh, no, I need parentheses around that, don't I? Have to be careful here. And then I'm going to say raise that up to the, now if I'm doing my second term, 2 plus 1 would become a 3. See that? So I'm letting n equal 2 here. And sure enough, you get 0.5, which is a fraction, is 1/2. See that? So that's a very tricky one. I think Mr. Clifford put that one together. Really like that. Well, the factorial symbol, hey, we've seen that before. You know what? Forgive me. We're going to have to restart the program because the calculator paused this. Factorial symbol. It's n times n minus 1 times n minus 2 times so forth. So 7 factorial is 7 times 6 times 5 times 4 times 3 times 2 times 1. Some of your problems might involve the factorials. By the way, let's talk real quickly. 1 factorial is obviously 1. We talked about this before. What's 0 factorial? 1, just in case you ever have to deal with that. Just a brief reminder. All right, well, let's go ahead and go to the next problem here.